Here's our next video on waves and oscillations, and I have description in the description a link for you that I want to watch before you watch this video. So the link will say watch also, and I want you to watch that video before you start watching this one. The other video is about 30 minutes, I think, maybe 35, and it's really important to understand the concept of this one. So again, you see angular speed and linear speed relationships and period, angular velocity, angular acceleration, the formulas that we did in our angular motion, and we will be back using these formulas again in this video. So the oscillations occur when the system is disturbed from its position of stable equilibrium, and oscillations are said to be periodic, and they display periodic motion. So if you have a spring and the mass attached to the spring and it bobs up and down or left and right, it's periodic motion. Or if you have a pendulum that swings there and back, that's also considered periodic motion. So sometimes they're called simple harmonic motions. And the frequency in the period we still can use for this motion, and again the frequency is the number of cycles per time or per second, and restoring force is the one that is making such motion happen. So if you have a spring, the spring force is the one that is helping the mass to bob up and down, and if you have a pendulum, then it's the force of gravity that is always pulling the mass to the bottom, and then because of inertia it continues moving to the other side and back and forth. So the circular motion and oscillations or periodic motion is can be looked at this as the same thing. This is why the formulas apply for one and another, and again this is explained very well in the video that I attached in the description called watch also. And we're gonna look at some waves reflections depending on the media that the wave is traveling through. So some of them call the hard boundary. That means if the hard boundary is there, that means like let's say right here, the rope is attached to the pole. So when the wave is going to the right, when it reflects, the bottom picture shows when it reflects, it's phase shift. So it was going this way. When it reflects, it goes phase shifted. It's called 180-degree phase shift. And if the boundary is soft, that means it can move up and down when the wave reaches the pole. So that means this part is not attached and can move up and down. Then the wave, if the wave was traveling this way, then it's reflected still in the same phase. And it also applies to the low and high density. So if the wave is traveling, let's say in this direction, and it reaches the higher density, part of the wave is going to be reflected the same as if it was hard boundary, and part of the wave is still going to travel in the same phase. So part is going to be reflected because this one is thicker or denser medium, then it's going to be reflection is going to be phase shifted, and the rest of the energy is going to be transferred to the thicker medium or denser medium, and that one is going to be in the same phase like you see in this picture. And when we have the wave is going from higher density, so here I have the thicker material and it reaches thinner material, we treat it the same as if it was the soft boundary. So wherever a wave is reflected, it's reflected in the same phase, and then the rest of its energy continues going in the lower density medium. This concept is very important to understand and remember, because we will be back to this concept when we start AP Physics 2 and look at how the light waves travel. So here is another example, and this one is called the superposition. And in superposition, and it's mentioned in your lessons through conceptual videos, in superposition, if you have, let's say, one wave is traveling in this direction and another wave is traveling in that direction, when they meet, so here I have, you see the green one, and I'm gonna make another one, the red one. When they meet, you see the yellow wave, and even though the red one is traveling to the left, to the right, and the green one is traveling to the right, after they pass each other, they will continue moving in the direction they were moving. But at the moment when they meet, they have a superposition, so their amplitude is rising. So that one is called the principle of superposition. And this concept again mentioned in your conceptual videos in the lessons that I posted for you online. So because the circular motion and wave motion or simple harmonic motion have the relationship that we can use the same type of formulas. So for velocity in circular motion, I have velocity is equal to the distance around the circle, which is 2 pi r, and divided by the time it takes to move around the circle once, which is the period. But in this case, your r becomes the amplitude. So in my picture where I have a wave, so this part is the amplitude. So I can replace it with 2 pi, the amplitude over the period. And so this is where you see the first formula for, this is for the spring motion, the mass in the spring. And if you solve this formula for the period it takes to travel one full revolution, or one full period of motion, then you could solve it and you have 2 pi, and again the amplitude divided by the velocity. You can also say that potential energy of the spring is equal to the kinetic energy of the spring that we used before when we used energy conservation. That means if I say potential energy, which is 1/2 kx squared, and in our case the maximum displacement is the amplitude, so I don't have to say x, I can say a squared is equal to maximum velocity 1/2 mv squared. Then 1/2 and 1/2 cancels from both sides, and when I look for the maximum velocity, then I will have that maximum velocity is equal to the square root of k over m. So this is where this formula appears from. This is not something that you haven't seen before. We used it in the conservation of energy, so you still can use this in this concept of periodic motion. Now, because the period is equal to, so because the period from this formula right here, let me do it in green, because the period is equal to 2 pi a over velocity, then I can plug in the equation that I just found for the velocity and solve it. So then I will have the period is equal to, this is for the spring again, the period is equal to, you have 2 pi a over the velocity, this is the middle formula on the top row, equals to, then I have 2 pi a divided by a, the one that I just found with the error, this formula, the square root of k over m, a and a cancels, and divided by a fraction is the same as multiplying by its reciprocal, so I have 2 pi m over k. So this is one of the most important formulas to remember in this section, the formula of period for the spring to make one full rotation of motion. So it's 2 pi the mass over k. K is the spring constant and the mass is attached to the spring. And if you see the time is going to be longer the more mass you attach to the spring. So the bigger the mass, the longer it will take to go back to its original position. So let's say in this picture you see the mass is attached to the spring. So the more mass is attached, the heavier it is, the longer it will take for the mass to go back to the original position. So the time is greater. But if the k is greater, which is the spring constant, so that means it will move the mass back to its original position, the bigger the k is. So with the bigger k, you get less time that it will take for the mass to go back to the original position. So the spring and the mass is one of the type of the periodic motion, and we just looked at these formulas and how to use them. We're going to look at the examples. And I also wanted to mention that angular velocity is equal to the angular distance, which is the angle 2 pi around the circle, divided by the time, the period. And I can rewrite this one as 2 pi, and 1 over t is the frequency. This is another very common formula that is used in many different subjects, especially in electronics and electricity. But if I replace the frequency with 1 over t, then I will have 2 pi divided by t, and I just figure out that formula, which is 2 pi, the square root of m over k. So 2 pi and 2 pi cancels, and I have the square root of k over m. So this is another formula that is given here, not given on AP exam. So there are a few formulas that are not given on AP exam, but you have to be able to derive them and understand where they're coming from. So if you understand where these formulas are coming from, you can always derive them on your own. So these were the formulas for the spring, and the formula for the string or pendulum. You also have to know this formula. I'm not going to derive it, it's just a little bit more complicated to derive it, but you have the period is 2 pi L over G, and L is the length of the string. So if you know the length of the string, then the period will depend on the length. G is the constant acceleration due to gravity, and 2 pi are two constants. And then again, if I use the same concept, I can figure out the angular velocity of it. That angular velocity is equal to the angle traveled around the circle, which is 2 pi over the time, and then you plug in this period and you can find what angular velocity is equal to for the pendulum. Let's look at this question and see if we can use this concept to apply to solve the question, the concept that we just talked about. 0.5 kilogram object connected to a light spring with a spring constant. So the spring constant is given and the mass of the object is given. On the frictionless horizontal surface, calculate the total energy of the system and maximum velocity of the object if the amplitude of the motion is 3 centimeters. So I can use conservation of energy. I have 1/2 kx squared is equal to 1/2 mv squared, and that's the maximum velocity, and x is your amplitude. So I cancel both sides. Calculate the total energy. I could do total energy 1/2. So that's the potential energy of the spring, which is 1/2. K is 20, and x squared is 3 centimeters, so 0.03 squared. That will give me 0.009 joules of energy. And again, coming back to maximum velocity, the velocity is going to be equal to the x, or the amplitude, the square root of k over m. So x is 0.03, and k is 20, and the mass is 0.5, which is 200 over 5, and that gives me 40. And I get 0.19 meters per second as the maximum velocity. And what is the velocity of the object when it's displaced only 2 centimeters? In this case, we will have again initial potential energy of the spring is 1/2 k and x squared, so that's the maximum displacement, which is 3 centimeters. And all this energy is going to be converted to the potential and the kinetic energy of both the spring and the mass. So I have potential energy of the spring kx squared, and this x is the one that is 2 centimeters, and then plus kinetic energy of the mass, which is 1/2 mv squared. They all have 1/2, so I can cancel 1/2. And if I plug in the numbers and solve for the velocity is going to be equal to 0.14 meters per second. They could also ask you to solve for the period of oscillation. So that would be a spring, so that's 2 pi, and then I have m over k. And if I plug in my numbers, I will get 0.99 seconds. And that means if you take a mass and you displace it from the equilibrium, so it takes for the mass to go there and come back 0.99 seconds under these conditions, the one that they gave you in the problem. And even though AP Physics 1 is algebra-based class, they do have sometimes questions related to trigonometry. And so like when we started math, we did the law of sine and cosine, and to solve problems with knowing that type of math. And the same for this concept. I'm not going to derive this for you. It would help you a little bit more if you watch the videos, the one that I posted in the description that says watch also. It will help you a little bit to understand how the formulas, where they're coming from. But it requires calculus to show how you derive displacement, velocity from the displacement, and from and to the acceleration. You have to take the derivatives. But we're going to skip this part. All you have to know is the displacement can be written this way, with the A cosine. A is the displacement, the maximum displacement or amplitude. Omega is angular velocity in the time. And then velocity is the derivative, which is calculus. And then when you take the derivative of the cosine, there appears a sine. Omega goes in front, so now there's not A alone, there's A omega, and then the cosine changes into sine, and you still have omega t. And then if you want to find acceleration, you take another derivative, and then another omega appears, the negative sign is still there, another omega appears and gives you omega squared, and now sine changes to cosine, and you still have omega t. So here is the question that I want to look with you at and explain to you how, with the limited math that you have, maybe some of you do have enough math to understand how these formulas are derived and to solve this question, and some of you don't. So let's look at this question and see if we can solve it. So a mass of 5 kilograms is suspended by a spring with which stretches 10 centimeters when the mass is attached, and then it gets additionally displaced by 5 centimeters. So at first we have the mass, and we place the mass, and it stretches the spring by 10 centimeters. So at this moment, I have the force of gravity is acting on it, and it stops. It doesn't bob back and forth. So, and then I have the force of the spring, which is kx. So the energy of the spring is kx squared, 1/2 kx squared. But the force of the spring, if you remember the Hooke's law, it's negative kx. Because it's equilibrium, I can set these two guys equal to each other. So I can say kx is equal to mg, and by plugging in, I will find that k is equal to 500 newtons per meter, because I will need to use it later because I need to calculate my frequency, so to calculate omega. Then I'm gonna look at, because you stretch additional 5 centimeters, so your amplitude is gonna be 0.5. So the ones that don't have the amplitude 0.5, I'm gonna cancel, and that's only A. That one didn't have amplitude 0.5. The amplitude stands right in front of the cosine. And I'm looking for displacement, so I only look for the first formula. And sometimes it can be cosine or sine, the first formula. But because they say, so if you have seen, the sine function looks like this, and the cosine function looks like that. So it starts with a maximum displacement, some maximum displacement, and the sine function starts from 0. And because in this case they stretch additional 5 centimeters down then your amplitude is -5 at the moment 0. So at the 0 moment, your amplitude is 5, and then it's going to be bounce up and down. But because it's maximum displacement, then it's going to be a negative cosine. So the amplitude is -5, and all of them have amplitude -5. Now I have to figure out what's inside omega t. And I also see that it is cosine. And this one does not have cosine, that one has sine. So I can cross the one out because maximum displacement only starts with a cosine. And then I have to figure out what omega is equal to and then plug it in. So omega is equal to 2 pi, the displacement over the period. So I have 2 pi, and the period of the spring is 2 pi, the square root of m over k. So I have the square root of k over m. And if I plug in my k and m, I will find that omega is 10 radians per second. Now, if I plug in into my equation, I will have, let me maybe erase this a little bit here. So I know it is cosine. So I have y is equal to, the amplitude is -0.055 centimeters. And then I have, and it's negative. And then I have cosine because the maximum displacement at the point 0 is present, so it's not 0. And then I have omega, which I found out is 10. And then I have t for the time, because it depends on the time. So from all these formulas, the only one that matches is, and I think there is, oh yeah, this one. It's E. So that would be the answer for this question. And I know these questions are a little bit more confusing, but I still want you to be able to recognize how to do them and to see little tricks that I just explained. So try to do this question again on your own through the lessons, not looking again through the video, and try to figure it out maybe a few hours later and maybe explain to somebody. Then you will understand better when you teach somebody else. Here's another question that I want to look with you at, and it is position of a time, and I have to figure out which one fits the description. So from here, I see that it's going to be sine for the position. So if the position is sine and the amplitude is 0.5, so all of them have 0.5, but it's positive. So positive 0.5, this one is negative 0.5, so that cancels. Also, only sine is left for displacement, that is right. And every single one of them have pi t. And if you remember from the formula above, when you take the velocity, extra omega appears in front. So in the sine changes right here, right? But it's only when it goes from cosine to sine changes to sine. When it goes from sine to cosine, sine doesn't change. So you see, when I went from sine cosine, the sine stayed the same. So if it was negative, it is negative. But if it goes from cosine to sine, then you do change the sign. It's a derivative rule. So if I come back over here, then if it was sine from cosine, sine changed. So sine doesn't change. So going from sine to cosine, sine, cosine, sine doesn't change. Sine, cosine, sine doesn't change. And then because every single one of them had pi t, then there would be an extra pi in front. So every single one of them has an extra pi in front, but this one doesn't. So this one doesn't have the pi. And if you look at the formula right here, do you see they all had omega t, and it stays omega t. It just changes something in front, but not inside of the parentheses of the sine cosine function. And the only one that doesn't change inside of the sine cosine function is a b. So that as difficult as it probably will get. I don't see it's going to be any more difficult than this. So we're going to stop these type of questions. You know, we won't see many of them on the AP exam. I haven't seen many of them on the AP exam. Here's one more question to look at. A simple pendulum oscillates with a period of t sub 0. If the mass of the pendulum is doubled, what is the new period of the pendulum? So the pendulum period is equal to 2 pi. You saw it at the beginning of the lesson, and it's L over G. And you can see that it doesn't depend on the mass. You can do wherever you want to do to the mass. It still stays the same. So the answer is going to be still t sub 0. So the period doesn't change. Here's one more question. The block of mass m is attached to horizontal spring with a constant k. So we have the constant k, we have the mass. The block undergoes simple harmonic motion, SHM, a simple harmonic motion with the amplitude of a. And which of the following graphs represents the elastic potential energy as a function of position? So the potential energy is equal to 1/2 kx squared. So when you have the maximum stretch, you have maximum potential energy. When x is 0, you have 0 potential energy. And when x is again stretched maximum, you have another maximum potential energy. And because the relationship of the potential energy and x squared, you know it's going to be a parabola. So the answer is A. So for the first one, potential energy, the answer is A. For the next question, the kinetic energy of the function, again, if you stretch maximum displacement at this moment before you release the mass, it has 0 energy, and then it goes back to this maximum at the equilibrium. When x is equal to 0, you have maximum kinetic energy because you have maximum velocity, and then back to 0 velocity when it stops about and change the direction. So wherever you lose the potential energy, it goes to the kinetic energy. So the answer so this was A, this must be B, because wherever you lose potential energy, you gain kinetic energy. And when you lose all the potential energy at x equals 0, then you get maximum kinetic energy. And the total mechanical energy of the system does not change. So the sum of every point, so at this point your potential energy is equal to some number. At this point it is 0. The adding these two numbers will give me at that position that number. At this moment your potential energy is 0, kinetic energy is maximum, so you get that number. And at this moment your potential energy is maximum, your kinetic energy is 0. The sum of it is going to be this number. So the mechanical energy of the system will not change unless you add and take away matter or energy from the system or into the system. So here is another question that you have. You have the mass attached to the spring constant is given, and how long does it take for the block to return to its initial position? So you have to calculate the period, which is 2 pi, and then you have the square root of m, which is 0.9, divided by 10. So that will give you mass over k. That's 2 pi, and you have the square root of 0.0909. The square root of this 0.3, so you have 2 pi times 0.3, and that will give you the answer of 0.6 pi seconds. I will stop our second video lesson on waves and oscillations at this point because I only have 1 or 2 minutes left before the video runs out of the time, which is 30-minute limit that I have. And I will continue in this next video. And thank you for watching this one, and follow the description of the video and watch the video that I hope you watch the video, and then in the description you see which video to watch next. And thank you, and I'll see you in the next video.